Well, good evening, ladies and gentlemen. My name is John Brown, and I'm the Treasurer of the Central Scotland Regional Group. I'm also one of this evening's speakers, but we'll get into that a bit later. On behalf of both the Engineering Group and the Central Scotland Regional Group of the Geological Society. Sorry. I'll try. I've got a little sore throat, but I'll try. Okay. What was I? Yes, on behalf of the two groups of the Geological Society, I'd like to welcome you all here to Glasgow Caledonian University. The university has been very kind to provide us with the facilities this evening, and particularly the School of Engineering and the Built Environment have provided the sandwiches that we've all been enjoying. Before we get started on the presentation, I do have a couple of items of housekeeping just to go through, if that's okay. The first thing is we have an attendance register, and I'll just pass that around if you can complete your details when it comes to you. The second thing is we are not anticipating a fire drill this evening, so if a fire alarm does sound, please don't be alarmed, but do leave the room to the corridor at the side, following the little green fire exit signs to the rear of the building. We'll all congregate at the back of the building, okay? Third thing is, the policy of the Central Scotland Regional Group at the moment is to record and present our presentations online. This is just because we've got a lot of members who live remotely from the Central Belt, so be aware that you and I are all being recorded. The other thing is, at the Central Scotland Regional Group, we're always looking for new volunteers to help us in organising these presentations, so if you're interested, please just find our details online and get in touch. And finally, if you have a mobile phone with you, as most of us do, please ensure it's switched off or in a silent mode. Okay, back to the important thing. The subject of this evening's presentation, okay, it's the fourth replacement crossing, which is a fantastic project to talk about, and we're going to have to keep ourselves quite motivated and disciplined to get through on time. We don't want to veer off track. We have four speakers this evening, so I'll just introduce ourselves. Paul Mellon, who will be speaking first, is the geotechnical manager for the whole project, and that's with Transport Scotland and the employer's delivery team on site. Paul's been involved in the project since 2008. The second speaker is myself, John Brown. I'm a senior engineering geologist with Arup, and on behalf of the employer's delivery team, I have responsibilities for overseeing the North Land and the Marine Cofferdam foundations, as well as the marine logistics for the project and the development of the port facilities and the upcoming cable-stayed bridge deck precasting operations. Our other two speakers are Iain Bews and Jenny Symons of Ramboll. Ramboll's part of the design joint venture, and Iain and Jenny have both been on site since commencement in 2011 as part of the designer's site representative team. Yeah, this is what we're going to try and cover if we can. We'll give an introduction to the project, some of the background, and some of the key figures and statistics in relation to the Queensferry crossing. I'll talk a little bit about some of the interesting features of the ground investigations, as well as the geology across the main crossing site. We'll talk about the role of the geologist on the project, the role of the pre-construction ground investigation, the formation inspection works that we undertook, the Central Tower construction works, as well as the trials associated with those works, and a similar section on the caisson foundation works. I'll then wrap up at the end with a bit of a progress update to show you where we've got to. Paul, if I can hand over to you now.
Thank you, John. Thank you, ladies and gentlemen. I'm Paul Mellon of Transport Scotland, the Scottish Government's transport agency. And together with Jacobs Arup, we form the employer's delivery team. And just to point out that I am a geologist as well, so we do have four geologists speaking this evening. To start at the beginning, the existing Forth Road Bridge is 50 years old this year, and there are a lot of celebrations, I believe, planned. It is currently carrying something like 5 or 6 times the level of traffic that it did when it opened in 1964, and every year the maintenance burden increases. On top of that, in 2004 to 2005, inspections of the main suspension cables revealed corrosion, leading to a strength loss of up to 10% in those cables. The more pessimistic predictions looked for potential for weight restrictions by 2014 and possible closure by 2019. I'm pleased to say that work since then has extended these timescales somewhat, but that lost 10% of strength is never going to be regained. So, with this situation, the Scottish Government appointed Transport Scotland to look at the feasibility of a replacement crossing. We looked at 5 crossing corridors along the length of the Firth of Forth from Grangemouth to Inverkeithing. We looked at 4 different structure types, both bridges and tunnels. But the preferred option, which was accepted by the Scottish ministers in December 2007, was for a cable-stayed bridge immediately to the west of the existing Forth Road Bridge. And by the way, the government wants it by the end of 2016, so a very tight timescale. At this point, Transport Scotland appointed Jacobs Arup to be our technical consultants to bring the scheme through the scheme development phase. I just want to say a few words about the employer's delivery team's approach to managing geotechnical risk. Obviously, a very important element is the ground investigation. The employer commissioned extensive ground investigations phased over 3 years with a view to amassing a robust body of geotechnical information that all the parties involved in the project could have confidence in. These investigations were carried out both on land for the approach road networks and in the Firth of Forth itself, but unfortunately we'll just be concentrating on the works in the Firth this evening. An important element of these phased ground investigations over a period of 3 years was a collaborative ground investigation in the 3rd year with the tenderers during the procurement competitive dialogue. And this was very valuable in giving those tenders some buy-in to the information, to the package of information that was being assembled, and helped reduce uncertainties when they were preparing their tender submissions. All data collected during the ground investigations was transferred to the tenderers electronically using AGS format where possible. And then when the successful contractor was appointed, reliance in all that data was transferred to him by means of duty of care letters, so he could contractually rely on that information. We also added to the employer's requirements, which form part of the contract, a requirement for a minimum scope of ground investigation by the contractor before construction started. This was really to encourage the contractor to get his own handle on the geological conditions out there and to develop his ground model specific to his detailed designs as they developed. 2 important employers' requirements that we wrote into the contract were, first of all, for the inspection of underwater foundation formations, sufficient to give the employer an assurance similar to that he would have had if the foundation formations had been inspected in the dry. This was a tall order, and we'll see later on when Jenny and Iain are speaking how the contractor tackled this requirement. And secondly, we also required trials of critical geotechnical processes before they were actually carried out as part of construction. And again, Jenny and Iain will describe how these trials were carried out to allow construction to proceed successfully, giving the employer assurance that the method chosen was going to succeed. And also, I suppose the contractor was able to demonstrate how he was going to do it effectively. Finally, just a brief word about teamwork. Transport Scotland appointed Jacobs Arup as our technical consultants to form the employer's delivery team. It was very important that we had continuity in the core team that was running the project, and this was maintained throughout the scheme development and into the construction phase. And also the integration was helped very greatly by the core team on both parties being housed in the same office. So that helped foster very direct communications, easy problem solving. We're pleased to say that we've been able to continue that approach into the construction phase. During the competitive dialogue procurement, we built up a relationship with the tenderers, and when the contractor was appointed, we've been able to continue that collaborative approach, that relationship with the contractor into the construction phase. And again, that has been very greatly helped by the co-location of the entire project team in the same office building on site in Rosyth. So just to put names to those titles, working from right to left, we've got Transport Scotland and Jacobs Arup together forming the employer's delivery team. Forth Crossing bridge constructors are the contractors who are responsible for the delivery of the bridge itself, and they have appointed a design joint venture of whom Ramboll are responsible for the foundations for the bridge. So what is the task ahead of the project team? They have to deliver what will be called, when it's opened, the Queensferry Crossing. It's over 2.6 kilometres long, of which over 2 kilometres is cable-stayed bridge. And if I can get this cursor to work, yes, I'll just point. Cable-stayed bridge runs from here to here. There's more than 500 metres of an approach viaduct on the south side over very shallow tidal water. There are 2 main spans, each of 650 metres, 3 towers, each over 200 metres high, and a total of 15 foundations from abutment to abutment. 5 of these are on land, the remainder are all either fully or tidally marine. Some of the challenges facing the construction team are that the spans cross 2 busy shipping channels to Grangemouth and Rosyth. The deepest water at foundation locations is at South Tower, here, where the water is 20 metres deep. The deepest rock head, also at South Tower, is 40 metres below Ordnance Datum. The tidal range in the Forth is 6 metres, and the tidal current at Central Tower, in the middle here, is 2 metres per second, which is a fair trot. I won't go into the geology. John will be describing that shortly. Suffice to say that a combination of the geometry of the bridge and the geology has resulted in a number of approaches to the construction of the foundations. All the foundations are spread footings onto rock, but they've had to be tackled in different ways. And we'll get some more detail about some of these later on in the presentation, but I'll just introduce some of the key locations for you. The yellow box surrounds the Central Tower foundation, which sits on a tidal island called Beamer Rock between the 2 shipping channels. Flanking that are the 2 north and south towers, plus an additional foundation of Pier S1, which are formed from caissons, large steel cylinders filled with underwater concrete. The remaining marine foundations are relatively conventional cofferdams, and then on land it's relatively straightforward. I would just draw your attention to the column on the right-hand side, and that 3 of these foundation solutions require the formation, the rock formation that's exposed during construction, to be inspected in the wet, underwater. And as I say, we'll see later on how the contractor has tackled this. I think at that point, I'll hand over to John to describe the ground investigations on the geology.
Thank you, Paul. Okay, move on. Okay, well, as Paul mentioned, we had several phases of ground investigations, both on the land and in the marine environment. We felt that this audience would understand what was involved in a land-based ground investigation and somewhat about the marine works, but we thought we would just touch on a few of our interesting observations that we encountered when we were undertaking these works. First of all, working over water is a new environment to many, and we thought it would be a good idea to get some additional training. So we actually came here to Glasgow, to the Glasgow Nautical College, and undertook some personal survival training. The image is actually showing the geotechnical lead for Arup getting slightly more than his feet wet here. The next interesting thing we found was we could swap our site Land Rovers for open-top speedboats. We thought this was quite a good idea, but of course, it being Scotland, it wasn't a good idea on every day. And then the general observation about overwater working in the Forth estuary was that we have access problems. you have to have somewhere to work from, and that can either be a floating barge, an elevated jack-up barge, or some sort of temporary structure. We've got a jack-up barge here, and you can see that it's elevated a significant height above the water, and it poses a significant challenge getting up on top of that. Paul mentioned again that there's a 6-metre tidal range here, so in this sort of situation you could find a 9-metre ladder climb to try and access that platform. There are means and ways of getting around such difficult things, but it's a whole subject in itself. But it is worth thinking about access when undertaking this sort of work. One other thing that we found was sometimes the simple things that trip you up in life, isn't it? On this platform, the contractor put land-based investigation tools. So there's a cable percussive rig and a rotary rig. And operating those rigs were standard drilling crews. And they were used to measuring the depths of their boreholes below ground level. And there's no ground here. So the contractor decided to survey the level of the deck and give them an offset that they had to take off every single measurement they made. It's not part of their standard operating procedures. They don't do it all the time. As soon as they became distracted or tired, it just went out the window. And it was something we had to keep a constant eye on all the time, was where they were recording the right levels. As you can see, we've got a cable percussive rig on the left-hand side of this platform, a rotary rig to the right, but pretty much central, and all of the equipment around about. Again, it's access. It's not possible to get all that equipment on the jacket when you need it, so it needs to be on before you start. And it just makes for a very, very congested workspace. And if you're an engineering geologist or a geotechnical engineer trying to supervise these works, you want to be positioning yourself where you can see what's going on. But it's virtually impossible to find somewhere to stand and see what's going on without being in someone's way at some point. Again, access restrictions. In the River Forth, we found that floating barges and jack-ups struggle to get to the shallow water areas, and indeed the deep water areas. We had, in the shallow areas, you can't float the barge in over it at high tide. So you can't access that area. In very deep areas like the South Tower, as Paul was describing, you need to have a jack-up with very long legs, or you need to use a floating platform, and then keeping that platform steady and stable and in the same position becomes a whole new problem. At Beamer Rock, we had ground levels at +2 meters OD, which is just below spring high tide, but a significant distance above low tide. So there was no option to float any sort of platform in over that space. We had to construct a specially designed platform that was light enough that we could lift into place with a multi-cat vessel. And again, even more constrained and exposed working environment for the drillers. Working over water, you're using boats and you're using barges, and typically these boats and barges are hired in and staffed on a 24-hour basis, so that ground investigation operation naturally fits into that and proceed on a 24-hour pattern. But it comes with its own challenges. First of all, lighting was very difficult. You can't have a working environment with some areas that are light and well lit, and some areas that are in darkness. It's just not safe. So adequate lighting has to be provided, and then you have to have extra generators. Well, it's all a problem. The next thing we found was that noise at night was a large issue. Calm sea conditions allowed noises to just transfer right across to our local residents all around, and we had to completely ban cable percussive operations because of that. It was just far too noisy, and even still we were receiving complaints. Paul will attest to that. So we had to address the rotary rig as well, and the way we got around that was by strapping rubber matting onto anything that moved or vibrated. Wow, it was sometimes dirty work. Actually, it was quite a clean environment to work in because there's no muddy fields to be traipsing around in all day. But if the borehole decides to start throwing up some mud, it's so congested, it's not really that easy to get out of the way of it. And you've got to admire this driller for maintaining a positive attitude in this condition. Yeah, and it was often tiring work, long shifts, night shifts, day after day after day. There's differing levels of good practice shown by these images. You could imagine that trying to have a quick nap in the welfare facility is slightly better than resting yourself in the drill rod rack, but we did have a word with the driller, but the photos are just too good, I had to keep them in. Okay. We'll talk a little bit about the geology now. Two images, the drift map on the left-hand side and the solid geology on the right-hand side. And this is the basic information we went with before we did the ground investigations. If we look at the drift image, we can see that on the south side we were anticipating glacial till deposits from the light blue colour, and 2 levels of raised beach deposits at this point in the fourth. And the only other information we could glean was that this green colour designated dolerite rocks at or near surface. When we look at the solid map, we can see that we should be expecting carboniferous rocks across the area, and these carboniferous rocks in the south comprise of the Calders member and the Hopetown member, and the Sandy Craig Formation in the north. They also pick up on the same doleritic rocks, however this time it identifies the dolerite rock as an alkali dolerite sill on the south, and a quartz dolerite sill at Beamer Rock and in the North Land area. In both images, there's poor definition, no definition of the drift and the solid geology across the marine area. So we did 3 phases of ground investigation over 3 years, and we pulled together some records on the encountered geology. We produced a 3D section to try and represent that, and the next few slides are sections of that zoomed in. And you can see the alignment of this section is right along the centre line of the bridge, cutting through the towers and the piers. We've removed any of the foundation details just for clarity. Okay, so starting on the south side, we can see that we did indeed find the glacial till identified by the light blue colour and the 2 levels of raised beach deposits. We also found granular fluvial glacial deposits and made ground associated with Port Edgar Barracks, a former naval base. But what we did find was that underneath the south abutment and Pier S8, we didn't have the alkali dolerite subcropping at Rockhead. We actually had Calders member sandstone. And if we move a little further offshore, we can see that this altered dolerite, the alkali dolerite sill, starts to separate into thinner sills. And as it does so, we found that the alkali dolerite became altered. So much so that by the time we get further out into the marine environment, it completely altered to what's known locally as white trap. And Iain will be showing some photographs of this rock later on. The other thing to see here is that we had identified a marker unit between the Calders member and the Hopetown unit, which was the Birdie House limestone. And that allowed us to get all of our stratigraphies right. If we had a borehole where we could identify the Birdie House limestone, we knew what was happening with the geology. And you can see that the bedrock and all the units are dipping just slightly more than Rockhead towards the north. And that meant that we actually found differing formation rocks at every single pier. So we would go from the Calders member sandstone into the Calders member mudstone, then the Birdie House limestone at Pier S4, then the Hopetown mudstone, and then the Hopetown sandstone. So varying geology for every pier. And above the bedrock we have a varying succession of fluvial glacial deposits, glacial till, and a thickness of alluvium, which all increase in depth as we go offshore. Moving further north, we can see the Pier S1 and the South Tower. In general, the rocks and the bedrock is continuing to dip towards the north. But noticeable here is that there's no dramatic drop-off in Rockhead. It just continues to drop at the same sort of rate as we move offshore. This was one of the very first things we tried to investigate at the South Tower location, because in a glaciated valley you might expect a steep drop-off in Rockhead. We certainly find that around Beamer Rock, in the centre of the river. However, boreholes here found the rock at around about -40 metres OD, and we did a few calculations obviously and worked out that that was adequate. We could form foundations at that depth. We didn't need to increase the span of the bridge at that point. So we kept the specimen designed to a 650 metre crossing, or span. Moving on to the central island, we obviously found dolerite rocks as expected below the central tower, but underneath we found that the carboniferous strata was actually more likely to belong to the Sandy Craig Formation of the north than the Calders and Hopetown members of the south. So that's a slight difference from the published geology. And then moving further north to the North Tower, we found a similar succession of alluvium over glacial deposits onto sandstones and mudstones of the Sandy Craig Formation. Again, we found another altered alkali dolerite sill, and we actually believe that that is the same sill as we encountered in the South Land. We found a volcanic neck just north of the North Tower, and a significant thickness of the Sandy Craig Formation tuff below the pier N1. And then when we move on to the North Land, there's a dramatic change in the geology, and we're back into the quartz dolerite sill that we encountered at Central Tower. In 2010, we did also identify a raised beach deposit in this plateau area here. And that's a summary of the geology. I'll hand over to Iain now.
Thank you, John. I'm Iain Bews. I've been working with Ramboll for about 6.5 years now as a geotechnical engineer, and the last 2.5 of those years I've been fortunate enough to be working on the Queensferry Crossing project, which is obviously an incredible project to work on. My role has been on the designer site representative team as an engineering geologist. Now, the designer site representatives are comprised of scientists and engineers from various disciplines, and our role is to be the designer's eyes on site. We communicate design issues between the designer and the contractor. We work closely with the contractor in order to help develop construction and inspection methodologies. We particularly get involved with design issues with temporary works, because we have to be sure that the temporary works are particularly complicated on a project like this. Obviously, large spread footings on bedrock may be complicated on land, but in a marine environment they certainly are complicated, and actually trying to get that foundation in place where it needs to be and ensure that the rock is cleaned and ready to go takes some doing. So, I mean, a good example of that is the jet grouting for the caissons, which Jenny will talk about later. We go out on site with Jenny or I are often, or other geological colleagues are often to be found on a barge next to a cofferdam, or indeed inside a caisson, inspecting the bedrock, making sure that it meets the design criteria, which again Jenny will talk about later. Sometimes John or a colleague in the employers delivery team may be accompanying us for our inspections, where John is looking out for the interests of the employer, Transport Scotland, whereas we, as the designer site representatives, we're looking out for the interests of the designer and making sure the design requirements are met. But of course, we all have the same objectives, which is ensuring that the Forth is bridged safely and that the high quality of construction is maintained throughout. Too far. Okay, I'm going to talk a little bit about the pre-construction marine ground investigation, following on from the earlier talk about the various phases. This was the final phase. Once the FCBC had been awarded the contract, they realised they needed to do a little bit more ground investigation, just to make sure there weren't any gaps, make sure that we had enough information to verify the design parameters, confirm the rockhead gradients, and of course also to satisfy the employer's requirements. In particular, there's an employer's requirement that every foundation had to have an investigation point in opposing quadrants of the foundation area, and that those investigation points had to be a minimum of 2 times the foundation width below the underside of the foundation, as per the Eurocode 7 guidance. So in the case of the South Tower, for example, which is a 30-metre diameter foundation, 40 metres below sea level, that means we have to go 60 metres below that. Hence, we were going down to depths of 100 metres, minus 100 metres below ordnance datum. So those boreholes weren't insignificant, and there was a lot of core to be logged. It was 24-hour working over 7 days, the same as the other investigations. It took about 7 weeks altogether. There was a fair bit of downtime due to some atrocious weather, as it was conducted between a sort of a November to a January period 2 years ago, as these GIs often seem to be, and we had some fun out there. Yeah. Nope, to get used to this mouse. We used the Geobore S wireline system for enhanced core recovery, which worked really well. In particular, the interface between the overburden, for example, glacial till, and the top part of the weathered rockhead, which often is lost because you the cable percussion can't get through that material, and often it can't be recovered by coring. Sorry, have I done something wrong?
No.
It's a relief.
Project it. Yeah, it's back on. I moved the mouse, it just went to sleep.
Thank you, John. Yeah, so here's an example of some intensely fractured mud. Oh, I should be using the mouse. And an example of some intensely fractured mudstone. You can see in this core on the wrist, you can actually pick out the structure of the rock, whereas without geobore it would have been almost impossible to recover that. It would have ended up just as a load of loose gravel in a box. I think I'm going to use the arrow in future. Okay, here's some nice core sticks. The top picture shows some sandstone. Nice, almost 1.5 meters of sandstone there, with no fractures. Second picture is some white trap altered dolerite, which John was telling you about earlier, intruded there into the mudstone country rock. And at the bottom you can see a contact between sandstone and mudstone, and you can see at the bottom right there in a section of sandstone there's a few centimeters of infill material. I should just mention as well that one of the reasons for the marine GI was the pre-construction phase was to get additional information about the fractures, because the fracture geometry obviously has a large influence on the rock mass strength. So rather than just relying on the predominantly UCS and point load tests that had previously been conducted, we did some tests on natural discontinuities, so we were able to ascertain a shear strength along natural discontinuities, which was helpful to verify the assumptions in the design model. Okay, there's some dolerite, 1.5 meter stick of dolerite, almost unfractured again. You could see that there aren't many fractures in it. The reason for that being predominantly because the dolerite was subvertically fractured, and so the two main joint sets were roughly perpendicular to each other and close to vertical. Therefore, it was possible to get some nice cores with virtually no fractures in them. Alternatively, sometimes you'll go right down the middle of a vertical fracture, and the whole length of the core stick would have a crack down the middle of it. But again, testament to the skill of the drillers on the recovery of the system that those cores were retained. Okay, I'm now going to hand over to Jenny, who's going to talk a little bit about the formation inspection on land and the design criteria that we were attempting to prove.
Hi, so as I was introduced earlier, I'm one of the engineering geologists from the design joint venture. So one of our main roles on the project was to carry out formation inspection, and it was essential for us to check that the founding rock, once it had been excavated and uncovered as part of the construction process, was consistent with the expectations of the design. So there are a number of key parameters that we had to check, and these parameters were related to the rock bearing strength requirements. So we had to check the rock type, the rock strength, the discontinuity spacing and orientation, the condition of those discontinuities, and also check that the overall formation surface roughness was consistent with the design. So was it rough, was it smooth, was it peaky, was it flat? So there's lots of things for us to check. We also had to check that the prepared formation surface was clean. Was it free of loose material, was it free of soft material? Because all these things would influence the performance of the design, of the foundation, sorry. And ultimately, once we carried out our formation inspection, we were able to sign off that formation. And we carried out this at each of the foundations. So, as previously mentioned, we carried out the formation inspection at the locations where the foundations were constructed in the dry, and also where the foundations were constructed in the wet. So this just shows you, again, the locations of each of the foundations. So we carried out dry formation inspections on the land-based piers, so near the abutments here and over here, and also in the shallow water marine piers, so inside the dewatered cofferdams, so here and here. We also carried out formation inspection in the dry at Central Tower, but Iain will talk about that later. This slide just shows you some of the environments we're working in. So the top two slides show Pier S5, before dewatering on the left and after dewatering on the right. And then below it is Pier S8 in a conventional type excavation with battered sides with the exposed formation surface ready for inspection. So you can see on the left-hand picture here, you can just see the guys actually cleaning the rock surface. They used jet washes, brushes, and there's a gully sucker as well, which is very effective at removing the last bits of the, sort of the loose material or any soil. And you ended up with a very good, clean rock surface we were then able to inspect. So formation inspection in the dry was relatively straightforward. We had full access to the rock surface, and we were actually able to carry out direct visual inspection. We were also able to carry out a scanline survey. And this was a really effective way of gathering data regarding the actual condition of the founding rock. It was a systematic way of gathering data. So we laid out a number of inspection lines across the rock surface, and along each of those inspection lines, for every discontinuity that crossed that inspection line, we assessed the spacing and the condition of those discontinuities. So were they joints or were they bedding discontinuities? We also looked at joint infill and general features of the joint. We also took orientation data of the joints and compared all the observations we made to those that were expected by the design. And back to Iain for some information about Central Tower and trials carried out.
Right, me again. Okay, the Central Tower. We're told it was the largest balanced cantilever ever built, which this diagram apparently shows quite well. We actually printed a copy of this and put it on the wall in the dive shack so that the divers could be fully aware of how important their work actually was during the inspection and cleaning. There you could see the location of the Central Tower on the beam of rock, which well, you've already seen numerous diagrams which show where the beam of rock is in the centre of the fort. And there it is in all its glory before it was blasted and excavated out, which I'll describe in a minute. That's the lighthouse, which obviously was dismantled. Now this is how the Central Tower was intended to look, and indeed now how the foundation does look. Around it's 25 by 35 metre approximate plan area with chamfered corners. All around the edge is a trench. Now the reason for the trench is that L-shaped cofferdam units were prefabricated close by in Rosyth and were moved into place by crane to form a watertight cofferdam so that the main foundation could be constructed in the dry. Now the majority of the geological of our involvement was in developing the methodology for inspecting those edges, because they could only be inspected underwater, because it obviously was in subtidal conditions and there was no cofferdam at that time. So okay, so I'll move on. Those are the cofferdam units being pre-constructed, well, having been ready to be taken out on a large shear leg barge and lowered into position once the whole of the trench had been excavated and assessed to be satisfactory. Now, the main part of the excavation was done by blasting, which had to be verified that the technique was suitable and that the blasting didn't cause any damage to the proposed formation level. Obviously, the blast had to take out all the required material without damaging the rock below, which then had to meet some quite strict design criteria prior to any concrete being poured. So an area of the foundation footprint was selected for a trial blast. Okay, is this the video, John? I believe it is. Okay. Come else do I? Okay, that was the trial blast. Not perhaps, it would have been nice to have seen that building flying up in the air, wouldn't it? But it wasn't. It was quite good at the time. Yes, so this is what was in place afterwards, following the blast. Detailed topographical measurements were taken of the pit and the extent of the blasting. In the foreground, you could see that the shoulder of the pit there was damaged a little bit more than was anticipated. It was only a very thin shoulder, which caused a few issues with our proposed inspection. Now we proposed to inspect the blast pit by a series of scan lines similar to what Jenny described as we did on land. Now, due to the water getting in over that shoulder area at anything except the very lowest tide, and also the excavation of the blasted material meant that the way it was excavated meant that some of the material got washed back into the pit at high tide. It was very difficult to get it completely cleaned out. So those factors resulted in it meant it wasn't really safe or possible for us to do these scan lines to the extent that we required. So we took the measurements that we could. You could see there that once the blasted material had been cleaned out by machine, you could see how it naturally broke back to the subvertical joint surfaces in the dolerite, and immediately beyond those the rock was solid with no signs of damage. So that was quite a good. The blast area was quite well contained in that respect. Now, because the scan lines couldn't be conducted thoroughly, we developed another methodology for formation, and we did that by bedrock coring. What else? So another jack-up. This time we did manage to get the jack-up floated over the beam of rock at high tide. It was an operation that was conducted at night, with being nudged into place by another barge. Really a real testament to the skill of the barge masters concerned that they managed to get that jack-up rig in that position centrally over the pit at night without being able to see anything, certainly not being able to see the rock because it was all underwater. And it had to be moved again twice because we ended up with three boreholes in that blast pit. That's a picture underneath the jack-up. You can see the drill string there centrally going down, access ramp there in the rear. And needless to say, it was a 24/7 operation over about 3 days. The moves could only be conducted on a very high tide, and at this particular time, the central tower was on the critical path for this project. There'd been a lot of delays due to bad weather and other factors, and at this particular time, we really need to get in and get it done. So it was done fairly intensively over a short period of time. There are some advantages for the beleaguered geologist who has to go out at all hours of the night and day. That is, you get to see sunrise over the Forth in the middle of winter, which is quite special. Okay, we did downhole geophysical logging in order to assess the naturally occurring fractures as opposed to drilling-induced fractures, because when logging core, you can obviously try to determine which is which, and if you're experienced, you can probably do it quite well, but there's always a bit of a question mark, and this sort of helps to reduce or eliminate that question mark. We used an acoustic and an optical probe. The acoustic probe was I think I'm correct in saying it was slightly compromised by the casing in the top part of the hole. There was a bit of interference. However, the optical probe worked extremely well. You can see a close up there of the probe. These are the results. We logged the core. We estimated what we thought were the natural discontinuities, and there was an interpretation made of the televiewer data, and there was a fairly good correlation between the two. So we were happy that the two methods in a way validated each other, and we felt that we gained confidence that the damage to the formation was, well, there wasn't any damage at the proposed formation level. The damage resulting from the blast was very shallow, maybe 100 mil, something like that. It certainly wasn't. It was certainly within the buffer zone. So, in fact, as a result of this trial, we extended, or in fact, we reduced the buffer zone because we were confident that the depth of blast damage was minimal. Following that exercise, the remaining 3 production blasts were carried out, which completed the area of the central tower foundation. Okay, so excavation of the central tower. Firstly, blasting, as I've just described. Secondly, excavation of the blasted material. The machines which were used for this process were all GPS equipped. So it was possible for the drivers to see exactly what depth and what level they were excavating to, which is how the tight tolerances, which are in the order of 15 to 20 centimetres, something like that, were achieved. That's what the dolerite looked like when it had been excavated and put in a pile. Most of the material was put on barges and taken away to be reused elsewhere on the site. Obviously, it's very good stone. It would have been a shame to waste it. And that's the milling wheel, which was used to fine-tune to get the formation exactly to a flat and even surface, again GPS guided to the correct level. Now, at various intervals throughout the excavation process, the level was checked by bathymetry. This particular survey, you can see that there's a slight high spot there where a bit more material needed to be excavated. So this was a brilliant way of making sure that we were on track and assessing when the correct level had been reached. Quite accurate results. Okay, so once the excavation had been complete, we had to inspect it. So it was inspected initially by vertical, again, what else? Coring. We did some 9 boreholes to 7 meters below the formation. Again, we used a televiewer, and again we analysed the fractures from the televiewer and the core logs, and the results again proved to be satisfactory. So that was a good verification that all the blasting hadn't done any damage to the formation. There's another drilling rig on a spud leg barge. This was the verification coring. And here are some more dolerite cores. We got to see a lot of core during this project. Right, following on from the coring, we inspected the formation using divers. There were 2 sets of criteria that we were hoping to prove, all required by the geotechnical design: the geological criteria and the cleanliness criteria. Geological criteria were, as Jenny has already described, with regard to fracture spacing and surface roughness, etc. The cleanliness criteria were making sure that there was no loose, damaged, fractured material, that everything that was there on that formation was solid and intact, so that when the concrete was poured, it was binding to proper intact rock, and everybody was happy that that contact would be effective throughout. So the trench area below the cofferdam units, you may recall I said that trench area around the edge where the cofferdam units had to be lowered down on, there was no way of inspecting that in the dry, hence the divers. So, comprehensive geological survey, followed by cleanliness survey before each cofferdam was lowered, and then a final cleanliness check using a camera on a stick, which I'll show you a picture of in a minute, before the concrete was poured. The comprehensive diver geological survey was done on a series of lines, as swimming backwards and forwards. The divers came up with a great system using, well, in fairness, we had some input into it as well, of jackstay lines and levelling staffs, and they were able to set out very accurately swim lines that were done at half-metre spacings. The spacing and the time taken depending on the visibility. There were times when the visibility was poor and the survey almost ground to a halt. There were other times when we made great progress. The whole procedure took many weeks, but it had to be done, and at the end of it, everybody was, I think I'm safe in saying everybody was 100% satisfied with that formation. We were sat in the dive barge. We, as I say, me, Jenny, one of our other colleagues, members of the employees delivery team, everybody concerned was keen to see and needed to see, in fact, that formation, that it was immaculate. And if there were any areas that we saw that we didn't like, that we weren't confident with, we'd highlight them, and the divers would have to go back in and clean them using the airlifting technique, which Jenny will describe later, or just levering out any loose blocks using a crowbar or similar. The divers carry a knife with them, not just for self-defense, but also actually for, we would ask them, we would say, oh, can you look at that piece of rock? Can you feel it with your hand? Can you loosen it? Get your knife under it. Is it solid? It was that kind of close engagement we had with the divers, with a live audio and video link, and every single fracture on every single line was measured by the divers and probed around with to our satisfaction. There's a dive barge in the nice beam of rock hole. There's the tranquil waters of the interior of the blast pit where the divers were sunning themselves. Sorry, diving. Here's the mission HQ. We would spend our time looking at the divers on those screens there, with the intercom down there. Try not to touch any of these controls. And there's a diver's umbilical and helmet. This is a video typical of what we could see. See there, the diver is measuring with the, he would put the staff along, and then he would measure at regular intervals from the staff the offset of any fractures and the width of fractures. And have a good old poke around with his knife. Okay, and these are a couple of stills taken from the video. You can see the excavation marks on the rock there. You can see the relief picking up some fractures in the rock there. Always looks better in real time than it does on stills, but it's worth taking them. They certainly look good in reports. It helps bring it to life so that everybody else concerned who wasn't actually there at the time can look at our monitoring reports and see that, yeah, we're happy, that looks good. There's a camera on a stick that I referred to. Immediately before the cofferdam units, well, sorry, after the cofferdam units were lowered, the final stage of inspection was, you can see the light, one of those is a light and the other is a camera. That was lowered down through the holes, which was subsequently used to pour concrete below the cofferdam units underwater. So this was the final check. And this had to be done immediately before the concrete was poured, just because the cofferdam units, once they'd been put in place, they were supported by, they had trench flaps and grout bags around them to make sure that no dirt or debris could get in underneath or be washed in with the tides. Well, because obviously the surface was completely clean when those units were placed. So this was just a final check immediately before the concrete was poured. And that was a high resolution camera. We could literally see grains of sand with it. You'd be showing the video to someone and they'd say, oh, there's bits of gravel there, and you'd say, no, that's sand. You could almost have eaten your dinner off that formation had it have been not underwater. It was a very high standard of cleanliness. And there's an example of one of the cofferdam units being lowered by the Atlas shear leg barge. Now, once all those units were in, hurrah, we had a dry formation. What we'd all been working towards. It was a moment of jubilation. You could see there being cleaned with an air lance. The rock's starting to come through, and Jenny and our other colleague Lauren, who we haven't mentioned yet, but she was also a geologist with us on site, are doing a scan line as they would on land. And that's it from me. Over to Jenny now to talk about the caissons.
So the caissons were a whole different ballgame, really. The three caisson foundations used on the project, North Tower, South Tower and Pier S1. Essentially the caissons were large cylindrical open-ended structures comprising a series of steel plates that were welded together. At the base of the caisson there was a cutting shoe, which is slightly pointed, which was used to actually cut through into the soil. The internal diameter of the caissons were either 24, 29 or 30 metres, depending on which tower or pier you were at. And there were had a double wall on the caisson, and there was either 1 metre or 2 metre in between the internal and external wall. So these caissons were used at the deepest waters, and the deepest rock head, as mentioned previously, was at South Tower, and that was minus 40 metres, or over minus 40 metres. So it's deep stuff. This is where the caissons were used. So you've got North Tower at the top here, South Tower here, and Pier S1 here, and their Central Tower. And you've got the two deep navigation channels here. So a little bit about the actual installation process. The caissons were brought out into position using a large floating crane, and they were lowered down onto the seabed. The caissons were then sunk through the superficial materials using a combination of ballasting and targeted excavation. So you can see a grab there that would be used to excavate the material from inside the caisson, particularly around the cutting shoe of the caisson. And this, as the material was removed around the cutting shoe, the caisson was able to sink down through the superficial material. And as John mentioned earlier, the superficial material comprised alluvium overglacial deposits. So you had fluvio-glacial material there, which was the granular material, and you had the glacial till, which was the cohesive material. And part of the sinking process was ballasting, so concrete was poured in between the internal and external walls of the caisson. This is just an example of some of the material that was actually brought out of the caissons. So once the material was brought out, it was placed in a split barge here, which was then taken up the river for disposal. So this is some of the alluvium here. And below that you've got the fluvio-glacial material from South Tower, and this is a giant boulder that was pulled out of the fluvio-glacial material at Pier S1. And you can tell the size of the kit that was being used on site. As you can see the man here standing next to the grab, and you can see it's pretty large. So that boulder was, I think, about 1.6 metres across. So as throughout the sinking process, as the caisson got lower into the superficial material, a temporary caisson was installed on top, and this was to prevent waves from overtopping into the caisson at a later date once the caisson had been dewatered. So throughout the sinking process, there was continued monitoring of the position, the planned position of the caisson, the tilt of the caisson, and the level of the caisson. And FCBC engineers, the contractor engineers, were monitoring real live data that was being brought in from the survey works. The slide on the right shows you the areas inside the caisson, and the actual excavation during the sinking process was targeted at different areas. And this was to ensure that the rate of sinking of the caisson was equal around the caisson. And so the excavation would, say, take place on the right-hand side for a couple of days. That part of the caisson would start to sink. The excavation would then change to, say, the left-hand side, and that would sink the left-hand side down. So it was a case of just making sure that the caisson was sinking at a consistent rate and was staying as vertically, but as near vertical as possible. Once the caisson was near the rock surface, jet grout columns were installed around the bottom of the caisson, and these were a key part of the caisson foundation construction. And these were essential in sealing the gap, really, between the base of the caisson, so the caisson cutting tube, and the sloping rock head. And so once they were in position, it was possible to carry out the final excavation down to rock head level using the grab and the airlift system. Essentially, the airlift was like a giant underwater vacuum cleaner. It just sucked out all the small bits that the excavator or the grab couldn't reach, and it cleaned the rock surface really nicely. So once that was cleaned, we were able to get in there and inspect it. Once that had been done, the underwater concrete was poured. So you can see the big underwater concrete plug here, and then the caisson was dewatered and the actual foundation was constructed in the dry. So jet grouting, as I said, it was a key part of the caisson foundation construction, and without it, it would not have been possible to excavate down to rockhead and clean the rockhead surface. So the aim of the jet grouting was to form a continuous wall of grouted columns, or you call it a grout curtain if you want to, around the perimeter of the caisson in order to close the gap between the horizontal toe of the caisson and the sloped rock surface. Just quickly, the process essentially involves drilling through the seabed until rockhead is reached, and then the drill head, the rotating drill head, starts to inject cement grout at high pressure into the soil. This effectively cuts through the soil, and as the drill head is withdrawn up towards the surface, you have a jet grout column formed. And essentially it's a kind of a soil creep type mixture, because the soil that's within the local area of the drill head, some of it's incorporated into the actual grout. So some boulders, some cobbles is actually incorporated into the grout, and it gets encapsulated. So that's how you form a jet grout column. So as I said, it's a key part of the caisson foundation construction, and without it, it would not be possible to dewater that caisson. And so it's essential that we carried out trials to ensure that the procedure worked out on the river. So the purpose of the trial was to define the jet grouting parameters that were required to make a jet grout column of a certain diameter. There was a design for the temporary works design for the jet grout columns, and there was a certain diameter that was required, and a certain strength of grout that was required to hold back the soil at the base of the caissons to allow that final excavation down to rockhead. So the main jet grouting parameter which was trialled was the total volume of grout that was actually injected into the ground. But other parameters were rotation speed of the drill head as the jet grouting was occurring, and the withdrawal speed of the actual drill bit. The location of the trial was on land, on the south side, and this area was chosen because there was both glacial till material and fluvio-glacial material, both of which are found out at the location of the caissons. So it was necessary to trial out the jet grouting procedure in geology that was going to be typical of what was found on the actual the site. So the two phases to the trial. The first phase was to construct 3 individual columns in both the glacial till material and the fluvio-glacial material, varying the jet grouting parameters between those 3 columns. And once those columns had been formed, the material around them was excavated, so you ended up with 3 freestanding columns. The diameter was measured, and the jet grouting parameters, the most appropriate ones to the most appropriate diameter were chosen for the next phase. So the next phase was to drill 3 interlocking, or to form 3 interlocking columns. And again, these were exhumed, and the diameter of these 3 interlocking columns were measured. strength testing was also carried out of the soil creep type material. I'll show you some pictures of those now. So these are the jack grout columns that were formed. The ones on the left were formed in the glacial till, and the one on the top right, were the three were formed in the fluvio-glacial material. As you can see, there are quite a few boulders and cobbles actually included within the jet grouting material, and the diameter of the columns formed in the fluvio-glacial material was quite variable due to the variability of the material that the column was being formed in. The column down on the right, you can see the bottom half is quite a consistent diameter, and then the top bit is a little bit wider. And this was where the column was formed through unweathered glacial till at the bottom, and then it hit the weathered glacial till at the top. So it was less stiff, and the material was less readily cut through during the jet grouting process. So that's about, I think, about 1.75 meters across the bottom one. This is just a picture of the interlocking columns. And so to test the strength of this material, horizontal cores were drilled through the columns to check that there was sufficient strength that was required by the design for the jet grouting works, and also that there was sufficient interlock between each column. So essentially we wanted to prove that the contractor wanted to prove that he could form a continuous wall of grout around the base of the caissons in order to hold the material on the outside of the caissons out. So the trial was a success, and the defined jet grouting parameters were taken into the main construction works. So this is just a picture of you can see the jet grouting rig on top of the caisson there, and all the jet grouting equipment that came with it. So during the actual construction works, there were a total of 65 columns drilled at North Tower in a ring, and at South Tower there are 184 columns formed, and then at PRS1 there are 74 columns formed. The glacial till, because it was a stiffer type material, narrower columns were achieved, and so it was necessary to have 2 rows of columns in order to form a sufficient thickness of grout to hold the soil out. The location and the verticality of the columns were surveyed and plotted up in AutoCAD, and where it was shown that there was a gap in between 2 adjacent columns, an extra column was drilled just to ensure you've got the continuous wall of grout. The verticality of the column was measured using inclinometers put down the original borehole that would form the basis of the jet grout column. As you can see, there are some that are a little less vertical than others. You can also see that there's an extra column there to essentially seal the gap and make sure you've got a continuous wall of grout. So in terms of underwater formation inspection at the caissons, it's a whole different ballgame to Central Tower. But just set the scene. Got the rock head down here. It's at minus 40.8 meters OD. It's a deep rock head. The water visibility in the caisson was pretty much near zero. The deep water precluded the use of divers for any sufficient time. The maximum time that diver could actually spend down at the bottom was about maybe 20 minutes. And so it was not possible to carry out a diver survey, as Iain had described, that we did at Central Tower. So therefore we had to come up with a remote inspection technique that allowed us to gather sufficient information about the founding rock in order for us to sign it off. So a special underwater camera was developed, and this became known as the camera dome. So again, as with the jet grouting and the trial blast, this underwent trials, and it also underwent a lot of modification. The early camera dome was a metal open-bottomed box with a camera and a light at the top, and this was lowered down onto the rock surface with fresh water flushed through from the top in the hope that we were going to be able to see the rock surface. Unfortunately, it wasn't very effective at keeping the dirty water out, and so it wasn't really satisfactory in terms of an inspection tool. So the next camera dome, a little bit smaller, but it was more effective. It was basically a perspex box filled with fresh, clean water, and had the camera inside the box and light as well. And this was again lowered down to the rock surface. There were jets around the bottom here, and these jets effectively flushed away any silt or any very fine loose material like gravel or bits of sand from the rock surface. And the principle of having a sealed box with fresh clean water worked. However, the size of the area of the rock that we're actually seeing was not sufficient for us to be confident that we just weren't seeing enough rock really. So these two images here show a before and after shot. So you can see the black material here is silt. This was before the jets were turned on. Once the jets were turned on, you could see the rock surface. You can see this is actually altered dolerite here, so it's the white dolerite. You can see a nice vein going through there. So it gave us really good images of the rock. However, we just weren't seeing enough rock. So the next stage was to make the camera dome bigger, and this was the actual final camera dome that we used to inspect the rock with. It's about 1 metre high and 0.75 metres wide. It's a perspex box filled with clean water with a camera at the top and a light, and with jets around the bottom to flush away any loose material or any silt from the rock surface. And this was a really good tool, and it worked. So it was lowered onto the rock surface at inspection points on 2 by 2 metre grids, and we were able to view the rock and to make observations regarding the parameters that I mentioned earlier, so fracture spacing, sort of fracture aperture and things like that. And we were able to make an assessment of the cleanliness. We did manage to supplement the camera dome survey with diver survey. However, as I said, divers were only really allowed to be down there for say 15-20 minutes. So it was really a case of the diver going down and trying to give us a general overview of the formation surface. But they were able, if we were unsure of anything that we saw through the camera dome, we were able to send the diver down. He'd be able to poke it, or even maybe bring a sample or something. So it was really, as a combined tool, it was really effective at gathering the information we needed to sign off the rock. The positioning of the camera dome, we utilised numbers and letters labelled around the edge of the caisson, and then we used wires going across the caisson to help us locate the camera dome. The two bits on the right, the top one, I think from North Tower, maybe South Tower, and that was, again, we used bathymetric survey to check that the formation level was at the right level. And the bottom right-hand picture just shows one of our inspection plans. All the green splodges are where we carried out the inspection using the camera dome, and these lines around here are where we carried out diver surveys or final cleanliness checks, where the diver swam around and made sure that the rock surface was clean. These are some of the images that we got through the camera dome. Top left is sandstone from North Tower. As you can see, there are discontinuities in there. You can see that quite clearly. You can also tell that the rock is solid and intact. There's a little pocket of silt there that the silt was caught in a hollow, so we couldn't actually flush it away on the first flush. The top right-hand image shows some grooves or some scratch marks that were made from the grab as it was excavating out loose material. So again, you can tell that's solid rock because of these grooves. And we actually sent a diver down to have a look at these grooves, and he was able to confirm that they were actually grooves. So he was able to give us a 3D perspective on some of these features. The bottom left, it's clear that that material is loose, so we're able to say this particular spot needs cleaning. We're not able to look at the rock, we're not able to see the rock here, so it needs re-inspection at a later date. The squares on the bottom of the camera dome are 100 mm across, so we're able to measure things, so we're able to tell fracture spacing, fracture aperture and things like that. In terms of data collection, again, we spent many happy hours in the dive barge. We also worked 24 hours, so we often did 12-hour shifts looking at this screen. we were able to actually move the camera around by 360 degrees, so we were able to really inspect specifically any feature that we wanted to, and we were able to zoom in as well, which was a really good tool. And we would record all our data on these sheets, so we'd actually draw what we saw, and then we were able to measure fracture spacing, and then we were able to measure also percentage that was unclean, or the size of any maybe loose, maybe the odd isolated gravel that we found on the rock surface. So again, it was really comprehensive data collection. And this is just a little video of what we looked at. So you can see the water is very clear inside the camera dome, and we're able to just move the camera around as we required. So different situations, Central Tower, but a very effective tool at gathering the information that we required to carry out our formation inspection and sign off the rock. So over to John, just for a quick roundup.
Thank you, Jenny. We're really running on with time, so I'll try and get through this quickly for everyone. A little progress update. Well, in the last year on the project, we've seen some really dramatic steps forward. You know, a lot of our work has been underwater and people don't see it, but now we're really seeing some visible signs of progress and some key milestones being met. We've made a little video of the last year's progress, and it can be seen at this YouTube link, although you can just find it if you search for fourth replacement crossing. I'll try and play the video if the technology allows during the question and answer session, but I've got a few images just to give you an idea of where we are currently. On the south side of the river, we have the deck sections. Both north and south carriageways are now being pushed northwards. Across, what we can see here is the south abutment bearing piers, and we're actually moving very close to pier S8, the first pier. So both carriageways will continue to be pushed northwards as more sections are brought in and welded on to the rear. The first couple of piers are well underway, advanced stage of construction, just as well because we're pushing the deck out towards them. An image now of the South Marine area. You can see the deck and the first few piers. The piers are actually being constructed in pairs, so the next two piers will come out of piers S6 and S5, which are accessed via a causeway. We then have a barge in between S5 and S4. Cofferdam at S4 has been installed, underwater concrete plug has been poured, and we're about to start commencement of the reinforced concrete foundation. At Pier S3 we've installed the frames for the cofferdam, but we're anticipating that the sheet piling operation will commence this week. There's a gap between Pier S3 and Pier S1 because we've not started S2 yet. S1 is the cofferdam that caisson, first caisson we've been talking about. Hopefully we'll be seeing that dewatered shortly, so we can start construction of the reinforced concrete foundation there. At the south tower, things are a little bit more advanced. We have poured the underwater concrete plug, constructed the reinforced concrete foundation, and we're on the second lift of the tower. Although, again, we can't see it yet because it's not out above the top of the caisson, but it will be shortly. Central tower, things are looking a bit more business-like. We've got the cofferdam installed, and you can clearly see. Okay, the jump form in place with the rebar for the next lift being put in place and the concrete already poured underneath. This jump form has now lifted up to that level. It's on the 5th lift today. North Tower is a very similar situation to South Tower. It is well underway, but we can't yet see the progress. And Pier N1, the cofferdam has been installed. It's still full of water, but we're hoping to dewater it shortly. And the North Land is well underway as well. The foundation for Pier N2 is constructed, and you can see here the north abutment is in an advanced stage of construction. So I just wanted to say that when we were planning to put this presentation together, I wanted to sort of say that there's four geologists talking about this project. There's been an awful lot more geologists involved, and we're not trying to steal all the limelight, but I wanted to put a list together and give credit where credit was due, and then I realised just how many people have been involved. So actually, the significant thing is that 85 geologists have been involved in this project over the time I've been involved, and that's just the number that I know of. I suppose the other thing that we should say is that geologists don't build bridges on their own. There are a lot of other disciplines involved, and of course we work very closely with geotechnical engineers as usual. and there's a lot of geotechnical engineers involved, a lot of other civil engineers, structural engineers, ecological, environmental specialists, health and safety people, transport planners. The list of disciplines just goes on and on and on. And really, actually, working with all these different disciplines and learning all the time has been one of the things that's made this project so enjoyable for me. We're now at the end, okay. But there, I will just go on to the next one. This is that presentation I was talking about. And what I'd like to do is just take questions from the room first, if that's possible. For the benefit of people online, I may have to repeat your question. So if you have any questions, please just let me know. Yes, I think that would be a good idea. You might have to answer something, Paul. It's like we're all lined up for punishment, isn't it? Go on.
What were some of the main problems?
Main problems.
Weather was probably the main problem.
Yeah, I think so.
Yeah, a lot of the work so far have been controlled by cranes, and so any wind, and even access. We've had a lot of access situations where we have to use a man-riding basket on a crane, and that just completely cancels work if the wind gets above 7 meters per second or mile. 12 for the cranes, but if you're man-riding, it's a lower threshold. So, yep. And we're at, because of where we are in the Firth of Forth, it's a narrow point of the river. That's why there's the bridges there. So it's a natural funnel for the wind, and actually the wind speeds pick up as they come across the, well, they come in from Grangemouth, most of the westerlies, so it's a difficult area for wind.
I think from a formation inspection point of view, liaising with the divers, it was quite difficult to start. A lot of these divers, obviously the commercial divers, they dive all the time. However, the detail that we were asking from their observations, they were used to looking at shipyard rules or just very basic general stuff. And so we were asking them to look at features that they possibly not looked at before. And so it was quite difficult at the start, wasn't it? Because we had to really kind of train them up as geologists in order for them to get the information from the client. So I think that was quite testing.
Also the contractors, the various guys involved in the cleaning and preparation of the land formations as well as the marine formations. A lot of them hadn't worked on a project before where such a level of cleanliness was required, and they would present the formation to us saying, well, that's okay. We say, no, it's not okay. Go back and clean it some more. And we look at it again and say, no, it's still not okay. It really needed to be immaculate so that we could be satisfied that the massive loads and forces that were being transferred onto those through those foundations could be adequate to transfer to the rock, and that all the design criteria were to be met. But once everybody understood that, housing contractors alike, then things started to progress a lot more smoothly because they just knew what we wanted and got on with it.
And I think you can extend that really to the whole project, because with the employers team involved, there was a period of understanding what the contractor and what the designer were offering to us, and them understanding what we were looking for. And I suppose that was a relatively slow process to start with, but once we got working together, everybody understood what we're supposed to be providing, what we were looking for. It made things a lot easier. And we do try and, although we're opposing parties in terms of the contract, there is a lot of collaborative working and trying to resolve issues early on, because what we don't want to do is stand in the way of the contractor's progress. So if we can work informally to resolve problems, which can then be sorted out formally through the contractual processes once we have a solution, that's, I think that's, we're reaping some benefits from that. But it took a while for the relationships to really gel.
One of the trials, failures significant, like the work done in various different trials. Was the client involved in specifying that in any way at all? Or was it a broad specification, you need to test the rock in terms of blasting, and then
It was broadly specified at the very beginning in the employer's requirements. Categories of work were set out where trials would be required. Basically, ground improvement was one of them, which covers a large number of techniques, including the jet grouting. But we specifically mentioned blasting. We specifically mentioned the underwater formation inspections. So there were specific areas that we wanted to be trialled. But basically, it was having established what areas the employer wanted to be trialled. It was a case of Ramboll and FCBC coming forward with proposals, and then we would work through, we would challenge them to ensure that the employer was getting something that gave him the assurance that he was looking for, which is something very difficult to write down from the beginning, but emerged from the discussions. And a lot of these discussions took place informally initially until it gelled to a sufficient degree that there could be formal exchanges of documentation to try and avoid them submitting something formally, which we would reject because we weren't happy with it, send it back again. So we've tried to work together to come to an understanding as to how the contractor and designer are going to resolve the trial situation, and that we were comfortable with it, and then that was a case of yes, go ahead and do it. But we don't specify precisely what we want. We challenge them till they produce what we want.
We just have to keep guessing till we get it right.
Well, that's part of the conversation, is to try and articulate what we're trying to achieve from this. And so there's quite a lot of dialogue involved. Sorry, Jim.
Yeah, well, I was just going to say that when we're writing the contract documents and the employer's requirements, we had to foresee what trial we may require. We didn't know exactly what the detailed design was.
There could have been piled foundations throughout. There could have been something completely different. So, of course. Well, we don't change it. We would set out, we want a trial of these particular things. So they had to have, their contractor certainly had to have in his mind what trials he was going to have to carry out and make a sensible estimate of the cost of that. Put that in. And point of fact, it may be that the contractor was wanting to carry out a lot of these trials anyway, just to give himself confidence that he could achieve what he was setting out to do. So I have no doubt that we didn't push them into a lot of these trials, that they would have undertaken them to their own satisfaction anyway. But it was just a case of not just the contractor's satisfaction, but also the employer's satisfaction.
Question at the back.
What was the design bearing pressure?
So that question was, what was the design bearing pressure at founding level? Have you got a particular look, just the maximum?
Yeah, I mean, the loading situation is quite complex. I'm really reluctant to just quote.
Yes, because there are a lot. In some cases, the foundation was designed for the temporary situation rather than the working or permanent situation.
I'm afraid we deleted that slide from this presentation, and we could have clicked straight to it and told you the answer immediately.
Design was
wrote it down and we've forgotten it.
Sorry, we can get some figures, and can we add it to the record or something?
Yes, we can. Yeah. That was a question about the issue of shallow gas?
Yes, in the sediments particularly, or? Yep. Mm-hmm.
Yeah.
Yeah. Well, I think there are two aspects there. There's gas in the alluvial sediments, and we encountered this very early on when we did bathymetric surveys and we tried to do some geophysics to pick up the rock head, and we found that there was gas blanking due to gas present in the alluvial sediment. So we knew that was there, and that was built into the risk assessments. But I think it never actually emerged as a live risk. We were aware of that, but there was no evidence that it was going to pose an actual risk to the works as the design developed. But secondly, yes, there's also gas was discovered certainly on the south side of the south abutment which we believe was emerging from the rock, probably from oil shale seams at depth, because on the south side of the river is oil shales, north side of the river it's coals. And so again, there was a risk assessment was done, and there was some change to the design of the south abutment itself, and the methodologies, the method statements for the construction of those excavations was took into account the possibility of gas. So we had gas measuring equipment available should it have proved a problem. But the measurements that we were getting from the boreholes were analysed, and yes, there's gas there, but given that they were working in open excavations, the risk was assessed out. Mm-hmm. But certainly, yes, there was gas detected.
Anyone else in the room? No takers? Okay. I think we do have a question from our participants online. The question is a similar question. Were any oil shale workings encountered in the vicinity of the South Piers or the approach? And workings, no. Oil shales, yes. The sills that intruded the area generally distilled off the hydrocarbon content of the shale. I think it's the Fells shale that we have on site, and it was really just driven off. So there wouldn't have been any advantage working those shales.
There were oil shales were encountered in the ground investigation on the southern approach roadworks round to the southeast of Queensferry, where the new M9 spur was constructed, and they had to undertake some grouting works when that was built a few years ago for the structure where the A90 goes onto the M9 spur, or is it vice versa? No, that's A90 onto the M9 spur. So that structure was grouted up, but our scheme starts immediately to the west of that, and the shale seams were dipping away, and the depth was such that no grouting works were required for our project. So we did encounter oil shales that had been worked, but that was at the very southeastern extremity of the project. And apart from that, we've had no mineral working. I have to say, in the north, to the extreme north, we did encounter some coal workings, which did have to be grouted. So when we were doing improvements to the M90 or the approach to the new crossing, we did grouting works there to improve that. So yes, mine workings were encountered, but not, as John's pointed out, under the main crossing because of the effect of those dolerite sills.
Okay. Well, it looks like that's all the questions we have online, and if there's anything else from the room? No? Okay, thank you everyone. Perhaps if you could just show your appreciation in the usual way, and